I would like to make my talk length being Schrodinger's cat. Depends on how fast I speak. And it might be a short talk or maybe a slightly longer talk. And this is joint work with Tom. And it has back to 2016. And then recently we make some progress. And we want to continue on extend this method to more general case. So here's the outline. We would like to derive Markovian reduced model for overdamped Langevin system. And at the same time, we develop numerical robust schemes. And in this talk, I will first briefly talk about the motivation. And then I will talk about, introduce how to develop a Markovian approximation in a naive way and for linear and weakly nonlinear overdamped system. And then I would like to discuss some challenges for the numerical integrators. And then I will give you a conclusion. So I think this slide, most of your audience are very familiar with. So we have, when we simulate a molecular dynamic system, in most cases, there are maybe a small portion of degree of freedom that really what we are interested in. And therefore, we want to reduce our full system to this smaller portion of degree of freedom. And there's no free lunch. Okay, so when you reduce the system from large scale to small scales, and you can imagine that originally you have a dynamic system, but after you reduce the degree of freedom, you will have something called the memory effects that are rising from the degree of freedom that you throw away. And based on the time scale between resolved and under-resolved, if we have significant time separation, then you can easily freeze these under-resolved variables and just study the resolved ones and derive Markovian approximation in a relatively easy and simple way. And suppose you don't have very clear scale separation, then you have to seriously take these memory effects into account. And sorry, I just list a few of mathematicians and engineers that I know their work, but I'm sure there are a lot of works developed for approximating these memory effects from chemistry and physics community. And forgive me, I did not put the researchers into this short list. And the motivation for our work is, suppose we have intermediate time separation, and we don't want to approximate these memory effects by a lot of computational cost. Instead, we still want to derive a Markovian model. Can we do this? And the answer is yes. So somehow for this intermediate and spatial varying type of simulation, we can derive a Markovian approximation by rescale the time appropriately, and the resulting model can capture both short time and long time statistics, as Sarah mentioned in the morning. So to introduce the idea, let's first think of a very simple linear overdamped SDE. So we choose this as benchmark is because we know everything about linear SDE. So, and we have the general solution and its equilibrium distribution. We also have the short time statistics because it's Gaussian. So long time equilibrium and short time ACF capture everything. Okay, so that's the reference, reference model and reference statistics. And then suppose we have a linear mapping that maps the entire degree of freedom to the coarse-grained one denoted by Cassie tilde. So this is just a mathematical trick because initially you just have a arbitrary linear mapping that project the full degree of freedom to the resolved one. And to make your mass analysis simpler, you want to renormalize the projection. So that's why we introduced the renormalized coarse-grained variable Kc. And then based on this linear projection, we can decompose the identity into two parts, the phi and the psi. And the phi denotes the projection to the coarse-grained variable, and the psi denotes the projection to the under-resolved. And then we arrange the original dynamic system to this one so that we can, formally speaking, separate the impact from the resolved and the under-resolved. And this new matrix contains all information compared to the previous A. Okay, it's just think of a different representation, but completely equivalent to the previous full degree of freedom, the full system. And then based on here, because Kc and Xi, they are separated, therefore we can represent Kc in a closed form only of itself. Okay, so here we have the exact equal sign, and the dynamics of Kc on itself depends on say initial condition of the under-resolved variable, and then the red term comes from the memory effect because we ignore the interaction between Kc and Xi. Therefore, in order to rewrite the solution, the system only in terms of Kc, the interaction from the under-resolved one will come into this memory integral. And the green one also accounts for the memory effect because we also throw away the noise, the thermal noise acting on the under-resolved variable. So when we derive the reduced model, this part will also come into the memory effects. And so in order to derive the Markovian approximation for Kc, that means we want to replace this time integral into some simpler differential form. And here's the idea how we approximate these two integrals separately. Let me first focus on how to approximate this integral I. And by the way, if you are familiar with Koopman or Morris-Wanzi, you probably noticed that at this point, this I and J, you can also formally derive from the Morris-Wanzi formalism by treating the thermal noise as external force. So you have ODE and then add on the external force. And then under that assumption, you apply the Morris-Wanzi formalism, you will get similar framework, similar expression for the SDE of Kc. So back to the approximation. So at this point, let's be less rigorous in terms of mass and make a mass crime here. That means we expand the S by time t. And then we formally can get this series expansion. And we especially pay attention to the first two terms. So the first term is as if we, sorry, there's a typo. We freeze the under-resolved variable. And if we keep the second term, it's as if we freeze the under-resolved variable along the orthogonal direction of the slow manifold, but let it relax on the tangential plane. So that's some geometric interpolation for each I1 and I2. And of course, you can keep more terms, but you notice that if you have two higher derivative for a stochastic process, then there are a lot of ambiguity if you want to seriously study the error effects. So at this moment, we only keep these two terms. And then similarly, we can approximate the J term, which is Ito stochastic integral. And notice that there's no derivative for Brownian motion. Therefore, we cannot directly Taylor expand the Brownian motion at time t. Instead, we first use the Ito formula, convert the stochastic integral into a time integral. And then, in a similar way, we approximate everything about t, and we only keep two terms. And there's another strong reason we do not keep more term is because the higher derivative of Brownian motion, at least for me, I don't understand. So at least for the first two terms, it makes sense. So let's keep everything together. So we first have previously I1 and I2, the truncation of the memory integral, and it's from 0 to t. And for the overdamped Langevin system, you have dissipated diffusion process, and therefore you can approximate 0 to t by negative infinity to t and apply Laplace transform. You can get a neat expression. And the same idea applied to J1 and J2. Okay, and depends on how many terms you keep. So let's record the original full system in terms of resolved and under-resolved variable, and introduce some notations that take each component of diffusion into account. And if I do not keep any term, say I approximate, I throw away all I1 and I2, and just evaluate the time integral at s equal to t, that will give us so-called approach zero. So physically, it's simple. That means you throw away all your under-resolved variables and only take a smaller system on the resolved one. That's called approach zero. And then if I keep I1 and the J1 term, this gives me approach one. That is equivalent to you freeze your under-resolved variables and compute the interaction between the resolved one and the frozen one. And approach two is you freeze the orthogonal part and relax the tangential part. And it's equivalent to keep I1 and I2. And notice that, so it's after we derive the approach two, and Tom noticed that approach two actually it's equivalent to rescue the time by the principal curvatures of the slow manifold. Because originally, if you have 40 in a system, your energy landscape is very rough. Therefore, everything scales slowly in order to have something interesting happen. And once you have less degree of freedom, the energy landscape become much smoother. That means the time scale become faster after we do coarse graining. Therefore, approach two is equivalent to you kind of estimate how much time acceleration you commit after you do the coarse graining, and then you pull back this faster time acceleration. So that's why it's equivalent to rescue the time by the principal curvature of the manifold. And then we have three approaches: approach zero, approach one, and approach two. So apparently approach zero is wrong because it's you throw away all under-resolved variables. And that will give you a wrong equilibrium unless the resolved and under-resolved are fully decoupled. And on the other hand, if we are interested in only equilibrium statistics, long-time statistics, then approach one and approach two will always agree for this linear system. And how about short-time statistics? Okay, so this is long-time statistics. But basically, want to say approach one and approach two both capture the long-time statistics, and approach zero is very bad. Then, in order to further compare approach one and approach two, we look at short-time statistics. And here, we consider the mean squared displacement, which is defined here. And we are specifically interested in the equilibrium ACF. That means we make the time lag tau being fixed, but let the observation time window goes to infinity. And then we can compute the MSD and the equilibrium ACF for both fluid dynamics approach 1 and approach 2, at least for this linear system. And based on these expressions, we can derive the error for each approach, and then based on the application, we can decide which approach is more favorable. So let's first talk about for all lag time, tau greater than 0. You can see that approach 1 compared to full system, the equilibrium ACF is approximately bounded by half tau squared, and then approach 2 is somehow in between. And that means approach 1 is always faster than the full dynamic system. And approach 2 is not sure because at the beginning, probably the rescale approximation by mean curvature, principal curvature is not accurate enough. Therefore, if I'm interested in short lag time, approach 2 is a little bit problematic compared to approach 1. And this also can see by rigorous analysis that for very short time lag, approach 1 have tau squared error compared to approach 2, which is only first order accuracy in terms of lag time. So in other words, if I'm interested in very short time statistics, approach 1, this simple approximation is much better than a more sophisticated one. And then another thing we want to study is how the time separation affects the quality of approximation. So in other words, we want to study the ACF error dependence on the spectrum gap. So we cannot study rigorously for a full n-dimensional system. Instead, we first consider a 2D system, and we make one reference eigenvalue to be 1, and the other to be greater than 1. So that means the first component denotes Kasi, and the lambda denotes the under-resolved one. And we assume our projection is controlled by angle theta. This is try to approximate the case if we can select the coarse-grained variable very locally to be the eigenvector, or we slightly deviate from the eigenvector. And then for under this setting, we can get the full 2D system in terms of lambda and theta. And we also define the average error rate of the equilibrium ACF, which is denoted by this L1 error rate. Then we can see that approach 1, the error of the averaged ACF will increase when you have larger eigengap, and approach 2 will decrease. So in other words, if I have a system with larger time separation, then approach 2 will be much better compared to approach 1. In fact, approach 1, according to the analysis, even hurt because the error of ACF increase when we have increased eigengap. And then we have the numerical study for the ACF result. I want to point out here they are all upper bound, means it's just a worst case. And in the simulation, it actually, you can see that for approach 2, we agree with our analytical upper bound, but the approach 1, our upper bound is way more loose compared to the reality because the ACF error become horizontal, not increase when the eigengap become large enough. So there is some mathematical interest to make the error bound even sharper compared to this one. So yeah, and then we also study the ACF error versus different time lag, as mentioned at the beginning. So here we all the solid line denote the approach 1, and the dashed line denote approach 2. And as mentioned at the beginning, that approach 1 will become better for the short time lag. So you can see that when time lag is very small, then I always have solid line lower than the dashed line, means the ACF average ACF error for approach 1 is less than the approach 2. And then when we have longer time lag, then approach 2 favors, because the approach 1 solid line always higher than the dashed lines. So in short, we consider this linear overdamped system, and then we first derive the closed form of resolved variable, and then Taylor expand the two integrals and compute the integrals up to 2 times. Then we can get a Markovian approximation. Next, we want to extend everything to a nonlinear case. And what we have done is we consider a weakly nonlinear case. So it's like a harmonic oscillator plus a small polynomial potential and controlled by small epsilon. And then if we just assume there's a unique local minima in terms of resolved variable, in other words, we have a unique slow manifold along the resolved variable Xi, then we can do the harmonic approximation along the slow manifold, and then we can turn to the potential to its harmonic approximation. And then we can get things similar to the previous linear case. And we want to mention that when we are talking about a nonlinear case, then our method cannot be recovered by Morris-Wanzi. This is because of the Ito's formula that brings trouble in all this chain rule. And in order to make our analysis similar to what we have previously, we convert the Ito's SDE to Stronovich SDE. And because we assume the diffusion is additive in the sense that it's a constant, therefore these two formulations are the same. And then based on the Stronovich SDE, we can do everything similar like the linear case. And we can get the approach 2 similar to the linear case. And here we have the Stronovich representation of approach 2. And you can see that it is still the time rescaling of the dynamics along the principal curvature of the slow manifold. Then when we consider the simulation, we cannot do Stronovich. So we need to pull things back. So we just apply the Stronovich and the Ito conversion formula, we can get the Ito formulation of approach 2. And similarly, we can truncate the previous integral up to I1 and J1 and got the Stronovich version of approach 1 and then pull back, got the Ito formulation of approach 1. So at this moment, we have approach 1 and approach 2 for both linear case and nonlinear, weakly nonlinear overdamped system. And I believe we can similarly study the error of long time and short time statistics. That's something mathematically we don't see many obstacles. But one thing we want to mention that the models we have, and we even can estimate the model error. But when we put things together into simulation, the numerics also brings trouble. So let's consider a very simple two-way model. It's just a 2D benchmark. So we have the linear contribution from just harmonic and nonlinear contribution that the nonlinear strengths denoted by epsilon. And we can just write down the approach 2 and the approach of this system. And I want to point out that at the beginning, we still want, so the reason we observe that we have to use Stronovich projection is because at first, we spend a lot of time ignore the Ito effect and only work on the Ito formulation and try to still mimic the Merz-Wanzi. So we can get this Ito formulation of approach 2. And then in the simulation, we found that we always get a bias, something wrong. And then we found, okay, it's because we ignore this Ito formula, and we should instead use the Stronovich projection to make everything work. Therefore, I want to highlight in the next slide, we will compare approach 2, the Ito one, and approach 2, the Stronovich one. And here's the result. So we consider a high temperature, beta equal to 1, and a weak nonlinear potential with epsilon only 0.5. So you can see that the pink one is the approach 2, but under Ito projection. And the blue one is the Stronovich approach 2. So, and because this 2D example is so simple, we can compute the exact marginal distribution of X analytically. And the red one is the reference. In other words, we run the 2D system with 4 degrees of freedom, and we can compare all the results. So on the left-hand side, we have the equilibrium PDF versus X, and on the right-hand side, we have the mean pass, which partially tell us the dynamic statistics. So apparently, Ito formulation is wrong, and the Stronovich projection is close to the truth, the sky blue one. However, we have some bias, slightly biased. Initially, we thought it's because our time step is not refined enough. By the way, we used Euler-Maruyama, and then we run very tiny step, 10 to the negative 5. We still see some bias of order, say, 5%. So definitely there's something missing in the numerics. And we run the trajectory, say 1,000, so that we also avoid the error due to the sampling. So in short, I think there are some numerical issues happened. And then similarly, we turn off the temperature, make a beta larger, beta equal to 10. Again, you see that there are some missing part in the approach 1, in the approach 2, and even the full dynamic system compared to the reference exact marginal. And again, because we use very tiny time step and enough trajectory, so this indicates there are some missing piece in the numerical simulation. And then let me switch a little bit from the modeling, coarse-grained modeling part to the simulation. So we note from this paper that if we have locally Lipschitz SDEs, which is the case we have the weakly nonlinear overdamped system, then explicit scheme, in this paper, they prove that all explicit schemes are bad in the sense that they may miss the invariant measure. If you want to have 100% correct long-time equilibrium measure numerically simulated, you need to use the implicit scheme. And here's a very easy cartoon. So the green curve is the exact PDF, and sorry, the color confusing, but the pink one is implicit backward Euler method with time step 5 times 10 to the negative 4. And this one, the wrong PDF is produced by Euler-Maruyama with time step smaller than the implicit one. And you see that it is far away from the reference exact PDF. So in other words, if you want to have 100% invariant measure, you need to use implicit scheme. However, implicit scheme is very expensive. So we want to think of, is it possible to combine the benefits of explicit and implicit together? We just use the common homogenization idea. So you can run implicit scheme for a short time. get a high quality, high fidelity data, and then you want to use inferred type of scheme, get explicit scheme based on implicit data, and then use this inferred explicit scheme to approximate a longer time. And in one paper that I collaborate with Wei Lu from Johns Hopkins and Felix Ye from U of Albany, we found this idea works when we have SDE with additive noise. It's very simple. So the inferred scheme is based on the classical scheme. So suppose you have SDE with additive noise, and you consider one step, and that's approximately, the numerical scheme is as if you approximate the flow map. And this is the classical EM and the classical splitting step stochastic backward Euler scheme. And they all try to approximate this flow map by this type of Taylor expansion type of approximation. Now, you see that for Taylor expansion, all these coefficients are determined. Okay, so how about we lose the restriction on these coefficients? Instead of determining the coefficients, we assume they are all parameters that can be inferred from the data. Then we can use explicit scheme as basis for inferred scheme and propose this inferred structure. And notice that it is very important to assume your residual is Gaussian white noise. And because of this assumption, we can prove that all these inferred schemes are reliable in the sense that they have controlled error under classical scheme. Otherwise, if we have multiplicative noise, we will not have this nice regression, residual of regression, and we will not have analysis. So for this, we can compute likelihood of each parameters, and then we can easily do some regression. So in short, here's a comparison. On the first block, we have the classical scheme used as our basis, like EM, hybrid Longa-Coulter-4, and SSBE. And then here we just have the inferred scheme. As I said, they look the same, except we just lose the constraints on the coefficients. These coefficients will be learned from the data, and we assume the residual are white noise. And so I skip a lot of benchmark examples in our paper, but I want to point out that with this inferred scheme, we can significantly increase the efficiency. So we have some 1D, 2D, 3D examples, and plain classical schemes will blow up at 20, 40, for example, and then this inferred scheme can improve the stability by 10 times. And however, as I said, this inferred structure right now only works for SDE with additive noise. And we are not very clear how to extend this idea to more general multiplicative noise. And I would like to discuss with you if you have any suggestions. So in short, here's the conclusion. So we just expand the integral representation of SDE, make some mathematical prime, and then can get approach 1 and approach 2. And one thing, just keep in mind that when you do all this Taylor expansion, you need to be very careful using the Stronovich. Otherwise, there are some systematic bias due to the Ito effects. And then secondly is we find that approach 2 have very nice geometric interpretation because it's reskew the time along the principal curvatures. So this opens the window to combine this large scale reduced modeling with this manifold learning techniques. So you can apply manifold learning to get batches of manifold for your system. And then for each batch, you can somehow compute the principal curvatures. And then on each batch, you can rescue the time. you just need to be very careful to jump from one batch to the other, but it is systematically, conceptually, it might be doable. And future work, as I mentioned, we want to long-time statistic and short-time statistic both simulated correctly. And at this moment, we want to see collaboration and suggestions to handle SDE with general noise. Yeah, thank you.